we can start our session today with the talk of Oleksii Rudenko about the relationship of volume and surface measure of small balls in Carnot group with the behavior of the Brownian motion in this group. Okay, please.
Yeah, just give me a second because I was just trying to correct some mistakes last second, which is bad idea probably. But my slides does not compile at the moment, so I do not have PDF. I made a mistake somewhere. It does not compile. So give me a minute. I find it, and it will be okay.
Okay, let's wait a moment.
Okay, yeah, I found it. It's just, yeah.
Very good.
Yeah, so give me one more second. I will open everything and we can start. Sorry for the delay. So this works. It's okay. So I will show you my screen. So today I want to give a talk about intersection of small balls with a submanifold in Carnot. So the idea, okay, so the name has hypersurface, but unfortunately it wasn't a good idea to put hypersurface here because it's often meant to have codimension 1, and for me codimension 1 is not very interesting, so it wasn't a good name. But it was just I just mixed up the terminology a little bit. I'm sorry. There is no good name that I can use. That's a problem, because if I use some manifold, I can use some manifold, but it implies that there are some additional structure here, which I do not want to assume. But let it be submanifold. Okay. So what I want to talk about now today is suppose that we have vector fields, which we can have any number of vector fields, but the values of these vector fields must have at least their linear independent vectors if we are in RD. Right? And then the commutators also have to satisfy such condition. This condition means that commutator can only depend on so we have degrees that correspond to each L. So P1 correspond to L1 and so on. And we cannot have that this sum of degrees of Li and Lj will be less than what appears on the right-hand side. So on the right-hand side, all degrees has to be smaller than sum. It will be clear why from the next slide. So this definition, by the way, is taken from the paper of Nagelstein and Wenger about Bose metrics defined by vector fields. And they assume exactly such condition on vector fields. And when you look at this distance here, so what we have here, we have that there is a multiplier delta power pi, which means that this curve can go in different direction with different speed. The speed is controlled by the degree of corresponding direction. And if, for example, we have vector fields Li and Lj, then it is well known. Then if we have coefficients depending on time, then we also can make this curve go into direction which is Ly Lj commutator. And if we have multiplication by delta pi, then of course this will be multiplied by pi plus pi j. Right? So this is why we need this condition, because if we do not have this condition, then commutators can be better directions than regional vector fields, and we do not want that. This is just not a good idea to define this. So we can just get rid of this situation and assume this. So this is the distance that I will be considering, and the question that I want to address is, suppose that we have, well, I say surface, maybe some manifold, right? It doesn't matter, but important that it's defined by such relation that is a zero set of some infinitely differentiable function, and its derivative is
Alexei,
non-singular.
Alexei, can I ask the question about the previous slide?
Yes.
Yeah. Here we defined such we always know that we have such phi, at least one, for some delta.
Yeah, so we have rank, maximal rank, so we can go any direction.
But we can go, but can we reach any point?
Well, assume that it's defined locally. I do not care about global problem. So
and it was proved in this paper that it is a distance.
Yes, of course. It was also in this paper. It was proved that this is a distance.
It is like a speed, like we have a different speed related to different vector fields. Yeah.
Yes. This is well. I also had a paper which considered such distance and similar problem.
Yeah.
They were the results was the most the first result in this direction.
In order to understand what will go further, at least. So it can happen that we can reach, for example, point y from the point x using, for example, some delta using L1, and at the same time we can take smaller delta and use L1 and L2 and so on. Yeah.
Maybe yes. So maybe we can have different curves, but with.
So maybe my question is much more about geodesics. Actually, can they say something in this paper about structure of geodesics in this space or not? Or it is not necessary? I think that it is important for you if you want to consider small balls. Yeah?
Well, it depends on what you want to know specifically. I don't think they studied something like this, but again, maybe it was maybe a question.
You see, I still remember very nice, but maybe very artificial pictures about Heisenberg group, where this vector field, as you already told us a lot of times, we have L1 is differentiation with respect to the first coordinate, so this is with respect to second, and finally L3 is commutator. I think commutator.
Yes, of the first two. I will give you this example later. Yes.
Okay. So we will consider this example. Okay, at least because I remember some very nice spirals or something. So.
Yeah. So the thing is, I want to give you one result which is general. And then I want to talk about some specific case also. So I start from the general, then I will talk about the specific.
Very good. At least have some imagination of balls and geodesics and this, I think, complicated from the first point of view distance. Okay, thank you.
Yes. Yes, it looks complicated, but I don't think there is a problem with reaching points because again we have maximum rank, so it shouldn't be a problem to find. The problem, of course, is to find the fastest. Yeah, this I don't know, but something is known already. So. In fact, something was proved in this paper, which I will talk about later. So what I want to do, yes, so this is what I want to do. I want to find the asymptotics of the some surface measure from the small ball. And yes, sometimes it is interesting to know if it's uniform or not. So if it's the same in the neighborhood of some point or not. Now to explain why I need this, yes, so I need a specific case of when we have Carnot group. So when we have Carnot groups, and we assume that we have exactly D vector fields, they are left invariant, and at zero we have coordinate vectors, and numbers also very specific, as I show you on the next slide. And yeah, so then example can be such group. There you can see the commutators of first L1, L2. We have L3, and other commutators are zero. And we can check that it's a group. And in this case, if I want to have a structure of Carnot group, I also put degree 1 to L1, degree 1 to L2, and obtain degree 2 for L3. And if for it to be a Carnot group, this degrees has to satisfy such conditions so that such durations is actually a group automorphism. We can check that in this situation with 112 that it works. It actually works from the form of addition. It can be seen. So here we have power 2, not power 1. Yes, and here. So on the third Carnot we have power 2, not power 1. Always. And the second condition, of course, that we have of all these vector fields, yeah, we only need those with degree 1. And if we have all degree 1, then we can obtain all the rest by commutators. So this is the last condition. And here I have to immediately recall the book where the definition of Carnot group is given, and even some potential theory for the groups is developed. So it is a very interesting book. I will not use some results from this, but this is where this definition is from. So I want to recall a little bit from my previous talks. So what I want actually to do is look at this intersection of function of several independent, and not just processes, Brownian motions on Carnot group. Yeah, so we have n Carnot groups and independent Brownian motions, and then we consider intersections of such functions. Yes, so joint intersection. And if we consider this, then we arrive to the fact that, in fact, we are looking at whether this process, this is multi-parameter process, visits such manifold M or not. And this manifold is defined by the equalities of such equalities. So if we have point on this manifold, it means that function 1x1 equal to function 2x2 and so on. So this is exactly a joint intersection of this. Without giving much more details, I will recall that there was a condition for the absence of intersections on some compact. Well, not just compact, maybe just any bounded set, but it is important that this condition involves asymptotics of both. Of course, it is a little bit more complicated than the situation that I showed you, but still, it is essentially more or less the same picture. We need to take surface measure from some small ball, and if we have this uniformly, then we obtain, of course, the measure new, I put the here surface measure, but it doesn't have to be surface measure, but if it holds for surface measure, it is enough. In the result, which is published, by the way, already, I can put any measure here to obtain the abscess of intersections. So as you can see, this asymptotics is relevant to the question of intersections. Moreover, I can show you another condition, which is sufficient condition for the existence of intersections with positive probability on an open set. So this condition is in form of integral. So here we again take measure, but then we also have to integrate over the same measure by the starting points. So it is kind of average asymptotics, not just asymptotic in one point. And then again, we have two boundaries like this. This condition is not present in this paper, but using the result of this paper, this condition can be it can be proved that there are some local times, and then there are corresponding intersections. So this is this condition. It follows from the result of the paper. So this condition is sufficient for the existence of intersections. So as you can see, it is interesting to find both estimates from above and below. And of course, this index nu means that we have to shift a little bit our manifold. But it doesn't matter much. Basically, it's just same problem with a little bit different manifold. So now I'll go back to the general case and try to explain my idea how to deal with this asymptotics. So suppose, yes, again, we have general case, we have some h0, some function, and consider all linearly independent families of such vectors. These vectors have dimension m, here, m dimension. Because we have f here. F is a function which has m value, m coordinates, right? So here we have a vector field acting on each coordinate of f. And here we have vector with dimension m. This family can be linearly independent because it has m vectors dimension m. And so we can find, maybe we can find such subset that this linearly independent. And we calculate the corresponding sum of degrees of all these vector fields for each such family. And so we take minimum of these numbers, and this is kind of homogeneous degree, sometimes they call. This is also can be found in literature in more algebraic problems, but yes, they have even some name for it, but I don't think it's. I should give some kind of name to this right now. So let it be some number, and so. For me, it's important that this number stays the same in some neighborhood of the point. Why? Because as you can see, so this condition that this is linearly independent is equivalent to the determinant of the matrix not equal to 0, which means that if it's linearly independent at a point, then it's linearly independent in the neighborhood. And so this number, it cannot jump. It cannot become larger in some neighborhood of x. So if we have mfx, then it cannot be larger, but it can become smaller. For example, if we have some set of vector fields that are dependent at the point x, but become independent for some y close to x, then mf can become smaller. And so And so this can be a problem, actually. This is what I think can be a problem. So this is why I call such points singular when this happens. So suppose we have in some neighborhood that this MF becomes smaller, so we will call such points singular. And, so the idea is to work in all other points which are not singular. And here I have to apologize a little bit, because in this theorem there has to be another side. So I have to also estimate from below. But unfortunately, yesterday, so the thing is, I prepared a new proof for this theorem to show you today, but I found a problem in this lower bound, which is unfortunately also the harder part. And I had to delete it for now. So I think it should be true that we have the same estimate from below, but for now, I just didn't prepare the proof for today. I'm sorry. Yeah, it's unfortunate, but at least I have the upper bound. So. So what is the bound? The bound is with power q minus mf. So basically, this is the sum of all degrees of all vector fields except this that we are selected. So this is very logical. Yes. So what happens is we have some vector fields that go along the surface and some vector fields that go away from the surface. So if we select those that go along the surface, the degrees has to give this power, which is very logical. This is intuitive explanation why we have such estimate. Okay, so what I have to say is that, of course, in Nagelstein-Wenger, they studied the asymptotics of both, but not surface measure, but Lebesgue measure. And so this is the case of x equal x, and they studied it and proved that it is just epsilon power q. So it is known. Also, here I want to recall, as I told you, there are some papers, algebraic papers in this on this topic of studying submanifolds in Engel group is this particular case of Carnot group. So unfortunately, most papers that I saw, they are for some partial cases, either for Engel group. Engel group is a 3-step group, so the degree can become 3, but no larger. And other papers that I saw also only degree 2. Maybe there was something else, but this also they also do something completely unrelated generally to what I'm doing, but in the process some estimates are similar to what I'm trying to do, so it's not exactly the same that I'm doing. I cannot explain the exact relation. So in order to prove this theorem, I will do the following. I will recall that also, by the way, in the same paper, Nagelstein-Wenger, yes, so we can define different distance, which is, I call, it is not always distance, because here it is harder to go from point to point, and we can have problems if, for example, the set is not convex, and inside the set, this is a problem to get from point to point. So it is not always possible. Unlike the previous distance, where we can always go around, here we not necessarily may go around. Because if we choose direction, yes, we go this direction. We cannot change. Mm-hmm. But it was proved that locally this distance is equivalent to the distance that I showed you on the second slide. So in fact, if I try to find asymptotics both the original distance, I can use this distance instead. which is very useful.
Alexei, am I right that rigorously your statement now about equivalence of the distance must be look like following? If we have that we have some neighborhood in which we can reach any point y, and we have some inequalities between these distances.
Locally equivalent means that for each point x there exists such neighborhood that in this neighborhood they equivalent.
But before you said that with this new definition, it is unclear, can we reach any point or not?
Locally we can. Locally we can. Because locally we can, we have...
Okay. This is exactly what I wanted to say, that we have a neighborhood in which we can reach any point, and this distance...
Yes, in this paper it was proved that we can reach every point in the ball with such exponential
Okay,
curve.
good. Thank you.
It is well known. So. So about the proof. So what I'm trying to do is just replace each point, the point inside function f, with its exponential with their exponential coordinates. So basically, a is an exponential coordinate of the point y. Not point y, the point that inserted here.
By the way, let me have a comment that this is exactly what I asked firstly. We have unclear geodesics, but now in your definition, locally exponential are geodesics, yes? So you now have a description of the ball.
Yes.
Okay.
Yes, this is why exponential... using exponential is very preferable. So another proof of this, so you may notice that I do not use here Carnot groups, but if you have Carnot groups, then we also have an equivalent distance, but this distance uses group addition. So of course here in general case I cannot use this. So this is why I do not have this result, because I wanted more general result and it just didn't work out. I think for Carnot groups I have this bound. So but here I have some problems for now. So the idea is that we change to exponential coordinates, and then we notice that in fact this is true. So the derivatives at 0 of g is equal to Lj f derivative by coordinate j. So in fact, linear independence means that the corresponding vectors are linearly independent, which means we can use implicit function theorem. And this is basically the proof. So all I have to do is to recall that surface measure, if we use parameterization, by all the variables except these ones. Yes. So and then we have we can write integral surface measure using such parameterization, and we obtain an integral, and we can drop all the relations, all the so here we need to have that coordinates, this coordinates is transferred to this coordinate. So here we have that AI less than epsilon power pi, right? So, and we can drop this for all this, and all the rest inequalities will give exactly what we need. So this will be just, since all the other inequalities is just give us a cube, no, not cube, but some something very simple. Yes, so we can estimate integrating by over this. It is very easy. We get estimate. So this is the proof in this direction. The proof in another direction is harder, because I cannot drop estimates on other variables, and I have to prove that this estimate on other variables follow from the estimate on these variables. And yeah, at the moment I do not have this. I cannot present this thing. So now I will go to more general case because I also want to discuss what happens in singular points. I will not discuss what happens in singular points in general situation. I have some ideas, but I do not have something. I decided not to pursue this also because I think it is possible to kind of avoid singular points, and the idea is exactly what I'm going to tell you next. So how to avoid singular points. Also note that it is easy to avoid singular points if we are talking about, let me get back to this condition. Yeah, so in this condition, it is easy to avoid singular points because we can just take non-singular point, and this is it. If we have in the neighborhood, if we have non-singular point inside here, yes, so it is enough, kind of. So I think that maybe.
By the way, that's the question: how many the singular points can be?
Yes, this is exactly the question. So this is what I'm going to try to at least some partial answer or some partial case. It is reasonable to assume that maybe the points where we have singularities are not so big, right? So not so large a set of singularities. But in general case, there is no way to kind of describe the set in a good way. That's why we have a problem estimating, working with these points. But in this particular case, when again we go back to this manifold M, when it is has specific structure, right? And then so this is it. And now also, okay, so I didn't tell you that, but in order to find the estimate that I need, I also need to change the degrees. So I do not use original degrees. Instead, I use degrees multiplied by some constant, which is constant is, well, it's non-negative. Well, you can assume that it's positive. For now, it doesn't matter. Different for each set of vector fields. So we have set of Carnot groups, set of vector fields. For each set of vector fields, we can multiply degree by some lambda. This is equivalent to the fact that we take in different epsilon. So as you remember here, so we have different powers of epsilon here, and we have on the other conditions the same, right? So this is why I need multiply by some additional constant. So because in this case, that's exactly what I had. And in fact, here I'm already going even out of this general picture that I showed you, because in the very beginning, I told you that degrees are integer. So in fact, in Nagelstein, Wenger, they assume that they're integer, but here they're not necessarily integer. So this is an additional problem, but luckily, the results, for example, Nagelstein-Wenger, I can use on each GI separately. So it is not a problem in that sense, but the situation is even more general. Here, fortunately, however, we have structure here, and I will try to explain this for the case n equal m equal 2. I think I can do something in more general case, but for the interest of this talk, and I think it's better if I explain it in the case n equal m equal 2. And besides, I do not have a full proof for general case yet. So let me consider case n equal 2, m equal 2. So what I have to suppose that we have a point which actually two different points, each one in RD. And we suppose that first is not singular for F1 and the second is not singular for F2 with the same vector fields. Then we look what happens if we try to at least study singularity, right? So we have to look at the such set of vector fields so that the corresponding action of null function f is the difference of f1 x1 minus f2 x2. So in this case, when I use this, yeah, then in fact it acts on x1, so it only acts on this part. And if I use L2, then it acts on x2, so only on this part. So when we study linear independence, we have to study action of L1 1 and L1 any index on F1, and for 2 we have to study action on F2. And since our M is also equal to 2, then we only have to select two vectors. These vectors have dimension 2, and we have to check if they are linearly independent. So because of our assumption, we have we have some optimal selection, and selection is the same in some neighborhood of X. Yeah. And the same can be said about F2. We have such selection of L21 and L2K2 so that they are linearly independent if acting on F2. And here is the same. And here I already have to use some structure because I assume that the first vector has index 1. This is because I start from this, because there has to be a vector of degree 1. And so I have to select at least one vector of degree 1. And well, okay, let it be the first. It doesn't matter, right? So this is why L11 here. Because if I do not have if I do not have vectors of degree 1, then all vectors of degree 1 acting on F1 is 0, which means all commutators of vector of degree 1 on F1 is 0, and so on. So all vectors acting on F1 is 0. So we have contradiction. So because of this, because of the structure of commutators, we have to have a vector of degree 1 here. So now assume that the point is also singular for M, but we have for some degrees, and it means that when we select vector fields, the optimal selection normally, okay, so we have P1 lambda 1 P1 1 lambda 2 P1 P1 and not lambda 2 lambda 1. This degrees that correspond to these four vectors that we may select. Selecting other vectors doesn't make any sense because it's not optimal. So we can only select from these four vectors. Here is 1, here is 2, P21, and here lambda 2, P2, K2. So what can happen is either we have to select these two, or we have to select these two, or we have to select these two, depending on lambda 1 and lambda 2. This is three cases. If we have to select this, then this selection is non-singular, as we already know. So this case is not interesting. The only case when singularity can occur is when optimal selection is this, but it doesn't work for some reason at the point. So this is exactly what I say here. It means that this has minimal total degree. These two first vectors correspond to minimal total degree, but they are linearly dependent. So, and also, yeah, also note here that this degrees has to be higher than 1. Otherwise, it is not very interesting because here this degree will be the same as this degree, and so again, we will not have singularities at all. So in this case, I can prove the following. So in fact, if we take the determinant of these two vectors, together, then I can find such direction that this direction goes along the surface F1, but also differentiating by this direction. In this direction, we have node 0. So what does this mean? It means that this function is determinant does not have singularity at this point. So in fact, there is if we write determinant equals to 0, this is a good also a good hypersurface, right? So all singularities lie on a good hypersurface. This is what this condition means. So this is exactly what I meant when I say that I know something about singularities here. I know that they lie in such set, yeah, and if this set is a good smooth set, then it is good. And this condition assures that if I take determinant and function f together, yeah, then together it is also nice function, which means that we have the corresponding set where it is 0 is also nice. And this is the point of this. So if we can find such direction, then it is very good from the point of describing singular sets. So we have a surface, right? So on this surface, we have some on this submanifold or something like that. So, and we have singular points only on this submanifold, and that's it. So we kind of know the structure of bad points. And if we look at examples, then it is so. So it happens so that we can consider function f with new function f with additional coordinate, and this new function f for these singular points describes all the singular points. Yes, and in fact, I think that I can reduce the question of existence of intersections the following form. I can take points outside non-singular points, solve prove that there are no intersections here, and then all I have to do is to prove that there are no intersections in this set of singular points. And this set of singular points is also a good manifold, so we can again use the same methods on this. So this is the idea how to prove maybe in general case. But it only works if we have if singular points form this nice submanifold. So let me prove this. Well, the proof is basically just again using the structure. So the main idea is that higher degrees of vector fields are linear combination of commutators of vector fields of degree 1. So in fact, at some point, when we take commutators, we will have to obtain a vector that will obtain every vector, yes, in particular this vector L1k. So eventually we will obtain taking commutators, we will obtain some vector that is linearly independent from L11. And it is in this particular case, I may assume that this vector is some vector from the set of vectors of degree P1 K1 minus 1. Because this is because exactly okay. This is the first time when we obtain this linear independence is when we have degree P1 K1. So when we have this vector field. So this is why it has to appear in this way. And also I have to take L11 because all other vectors of first dimension, they are parallel to the surface. So taking commutators with them, we stay parallel to the surface. So they cannot produce something not parallel to the surface. So we have to take L11 here. It is a bit intuitive explanation, but I think I can prove it rigorously too. So this is, yeah, so here I'm maybe not give you complete proof, but I think this is true that this such vector exists. that these are linearly independent. And if this is true, then we can we note that since L11 optimal selection, then in fact this vector L1R is linearly if after acting on F1, it is linearly independent with L11, and it happens in some neighborhood of X because everything happens in some neighborhood of X, as already mentioned. So this means that this is exactly the direction that we can use, because if we use it, then we can see that here action of this vector field on this vector field is commutator plus action of the opposite direction, and action of the opposite direction is 0 because this vector field is 0, as I told you. So this is 0. This what remains. And we can drop this part because it in this part we only obtain something that is proportional to L11 F1 in X1, nothing else. So we obtain this, and this is not 0 as I assumed. So in this way, I found a direction which derivative is not 0. Yeah, so this is my idea how to maybe deal with the singular points, at least for this case where I have this particular surface M and the structure of vector fields. For today, I think this is all I prepared. So this is all.
Okay, thank you very much for interesting talk about such a complicated object. And maybe somebody have questions or comments, please. I have several questions. And the first one about this characterization of the set of singular points. In your partial exams, which you showed us, it looks like the set organized some submanifolds of smaller degree. So it has like surface measure on the initial manifold equal to 0.
Yes.
So maybe there exists some analog of Sartre's theorem for the case of for this case. Maybe due to some degeneracy at the singular points, we can always say that at least the surface measure of the set of singular points is equal to 0.
Maybe, but I do not know how to do this.
Because actually all this stuff is very similar to the classification of singularities in the usual surface measure theory, like in when we consider usual Hausdorff measures and Lebesgue measure. This is the first question. Another one, how these distances, you propose us two different distances. One is really distance, another one related to exponential mapping, and also locally is a distance. And they are related to the vector fields. And of course, if we consider now the solution to Stratonovich differential equation governed by these vector fields, we get a Brownian motion. And in this, in case of Carnot group, this is really a Brownian motion in Carnot. So maybe there are a lot of already known facts about the local behavior of the Carnot, of the Brownian motion in Carnot, like this. For example, how this small balls, how this distance is related with the Brownian motion. If we have usual Euclid case, Euclid finite dimensional space, we know, for example, the asymptotic of the time of exit from the small ball. We know that existing measure on the small ball is a uniform distribution. So what do you know about the same relation in Carnot group? How the behavior of Brownian motion in Carnot group is related to the geometry of the balls which you propose us? I think it must be related.
Yes, of course, as I showed multiple times, it is well known that density of the Carnot, of the Brownian motion Carnot group
Yes, is
can be
estimated.
estimated.
Yes,
Yes.
yes, I
And so we
remember
know
this.
how potential behaves like the distance
Exactly.
and some power. Yeah,
Yes, I remember this, but
this is known.
for example, what can we say about the exit measure from the small ball? Is it close to Hausdorff measure on the sphere or not? Something.
This I do not know, but I have to say that the closest thing to what you ask is maybe this book by um, they do some interesting things that very similar to what is done in Port Stone, I believe, not exactly, but in some parts. And also, well, they have very different approach. The approach is not probabilistic. They use Dirichlet problems, but it seems that some results look similar to they have some explicit formula for some objects that are related to usual potential theory for Brownian motion. It is a very interesting book, but I did not have an exact use for the results, and because they're not probabilistic, the problem is to relate them to actual process. So maybe sometimes it's not completely obvious that that it is related to the process because it's related to a potential that they use.
And it is related to very natural, but maybe in such complicated situations, this question cannot be solved. The question is following. For example, if we consider Euclidean space, then suppose that we have not Brownian motion, but consider diffusion process. Then we mentioned this result a lot of times. Maybe Molchanov, Stanislav Molchanov first proposed to consider Riemannian structure on the Euclid space related to coefficients of diffusion process, such that operator Laplace-Beltrami operator of the obtained Riemann manifold is exactly a generator of the diffusion process. So let's go back to Carnot group and Brownian motion here. Is this metric which you propose us natural for Brownian motion in Carnot group? So what will be like generator of Brownian motion as a Markov process on Carnot group with respect to this distance? Yeah?
No, the relation is not to the distance, but to vector fields. And if we look at this Carnot group structure, then I already mentioned that we have sum of squares here. If we take sum of squares, and this is a generator of corresponding.
Yes, we have a generator, but you see, you have a distance, and I think that you have some differential structure also on this Carnot group related to this distance. Of course, it can be described in the language of the vector fields. But
I believe it is known that if we have process for more general Li like this, then this distance, corresponding distance, is related to the process. But I do not recall exactly where I saw this, but I believe I saw this. This is partly known. Maybe not exactly kind of relations that you want, but some relations are known.
Okay, so this is natural distance. It means that the Brownian motion has a different speed in different directions, yes?
Yes, this is exactly the idea. Intuitively, it is true, but proving anything is the question.
But still, the speed must be comparable. Like
No. You see here. The problem is that for each, what happens? We can only if we have diffusion, then, and we have directions, and diffusion in this direction has always speed 1, right? So to obtain speed 2, we need to have two directions with speed 1, and this direction with speed 2 is a commutator of these directions. So this is what happens. And we have if we have another direction with speed 1, it can commutate with direction of speed 2. It produces this direction of speed 3. And we obtain this I already showed you before. The corresponding process will be just multiple stochastic integrals.
Can be represented as
Yes. This is 3 times integral. This is 2 times
but you
integral.
See, if we can, okay, let's try to use this coordinate description. Then we have for the Brownian motion, for one-dimensional Brownian motion, we have law of iterated logarithm. For multiple integrals, I think there are a lot of works about its asymptotic at 0. Yeah. So why don't to try to characterize these singular points with such point of view that we have some directions where we have different speed, different upper limits with different asymptotic for our Brownian motion. Yeah?
So you propose to try to look at singular points from the point of view of the process. What happens to the process?
Yes, exactly. How it behaves locally in this.
Yes, I had an idea about this, but I did not do anything in the direction yet. So maybe it's interesting.
Okay. Thank you very much. It is very interesting, and I think very perspective object because it contains a lot of differential geometry, and from other point a lot of multi-dimensional Brownian motion theory. Okay. So for today we finished our job, and who is the next speaker, Georgi?
Вадим Радченко.
Okay, I think it will be talk about the random measures and partial differential equation.
Exactly.
Okay, so thank you very much, and everybody, bye, and see you next week.
Bye.
Bye.
Thank you, bye.